as you can see here, we have a nice river, and we're going to try to build a three-sided fence on the side of the river. But we want to build in such a way that we maximize the area in here. To do that, we can use a little thing called optimization. So the max amount of fencing we can use is 500 feet because labels are important. Now, the perimeter equation is all the sides added up will equal this. So I modeled it by 2a plus c is going to equal the perimeter. We can also find the area by multiplying this side by that side, a times c. What we're going to do here is we're going to solve for a variable, and the easy one to do would be solve for c. Excuse my poor handwriting. Subtract 2a from both sides. C is equal to 500 minus 2a. Now, we could come in and substitute that for c. So area is going to be equal to a times 500 minus 2a. We're going to distribute that. Big A equals 500a minus 2a squared. Now, to maximize the area, we're going to take the derivative of this. So dA little a equals 500 minus 4a. We're going to set that equal to 0 to find the critical point. Minus 500 is 500. And solve for a. A is going to be equal to 125. Now, we're going to take this value and plug it back into our original perimeter equation to find c. So 500 equals 2 times 125 plus c. 500 equals 250 plus c. C is going to equal 250. Now, we can prove that this is the maximum value. We can prove that this is the maximum by taking our derivative and taking its derivative again. So this will cancel and that will cancel. So our second derivative is equal to negative 4. This tells us that for all values, so because our second derivative is less than 0, we know that the entire function will be concave down for all numbers. So, which shows that at this point, there's a maximum. Which means we found the maximum area for our little fence. So now that we proved it had a maximum at a equals 125, we're going to find the area. 125 times 250. Total area is going to equal 31,000 feet and 31,250 feet squared, because labels are important.
Okay, so here we're trying to find what is the biggest rectangle that can fit under the parabola. Oops. Okay, leave that. Okay, so first to find this, we have our function, which is negative 2x squared plus 12, which is right here, and then the area of rectangles, base times height. So the base of it is going to be 2x because you have x over here and x over here. So the area equals 2x, and then the height will be the function. And we're going to distribute. Okay, then from there we're going to take the derivative to find the maximum rectangle. And then set that equal to 0. Now then you can divide by -12 because it's set equal to 0. So then you have, wait, you're going to just divide by 12. -x squared plus 2. So then from there you can move it over. You have x squared equals 2. Okay, so then you take square root of 2, which it should be plus or minus, but since we're doing area, it wouldn't make sense to use the negative number, so we're just going to keep it positive. So to prove that this is the maximum, we're going to bring it over here on a number line, and so logically it's going to increase here and decrease here, making it the maximum. So to find the total area, I'm going to plug it back in here. So for base, we're going to have 2x, which is 2 times the square root of 2, and then your function, which is -2 square root of 2 squared plus 12. So that is 2 square root 2, okay, sorry, which is 8. And then your final answer will be the area is 16 square root 2.
Nice. Alright, now that you saw our example videos, you can give this one a shot. So pause now, and in a little bit we'll have the solutions up on the screen. And here's the solution.
And here's an example of another one. This one's a little different, but you should still be able to figure it out using optimization. And there's the answer.